Next up, I'd like to invite Clark Chapman to the stage. Clark Chapman is a planetary scientist whose research is specialized on asteroids and creating planetary surfaces using telescopes, spacecraft, and computers. He's past chair of the Division for Planetary Sciences of the American Astronomical Society and was the first editor of the Journal of Geophysical Research, Planets edition. So it's also worth noting that he is the recipient of the DPS's Carl Sagan Award for Excellence in Public Communication. So thank you for joining us here.
Thank you.
Well, we've already heard a little bit of the basics about asteroids, but actually maybe we could start by bringing up, we had mentioned comets earlier as well. So what's the difference between an asteroid and a comet, and do we have to watch out for comets as well?
Well, the difference between an asteroid and a comet, there's several kinds of differences. One is, as has been said, asteroids are points of light and you need telescopes to see them, and comets are made, asteroids are made of rock. Comets have a lot of ices in them, and when they get close to the sun, like inside the orbit of Mars, then the ices start to evaporate and you get these enormous tails, and so people can just go out in their backyard when a comet comes around and watch a comet for weeks or months as it's near the sun. The other difference is that most comets are believed to have formed outside of the planetary system, maybe beyond the orbit of Neptune. At least that's where they were early on. They may have formed somewhat closer to the sun, but then they've been stored in orbits beyond the orbit of Neptune in the far outer reaches of the solar system where it's very cold, which is why their ices, water ice, dry ice, and so on have remained. Asteroids located in this asteroid belt between the orbits of Mars and Jupiter are in a pretty cold place by our standards, but warm enough that ice doesn't last for 4.5 billion years.
So you talked about ices versus rocky objects. How do we tell what these objects are made out of?
Well, that's actually something I worked on for my PhD thesis many years ago, was using telescopes with a spectrometer that measures the colors of the reflected sunlight from asteroids. And if you do this with rocks on the Earth, different minerals, like the olivine that we heard about from the stony iron meteorites, peridot, has very prominent absorptions at certain wavelengths so that we can see, we hope to see, what they're made out of. Now, a lot of asteroids, as have been said earlier, are very dark and black in color, have a lot of carbon in them, and that kind of suppresses these wavelengths features, and so it's a little hard to tell what a lot of asteroids are made out of. But in terms of comets, we can see what the tails and atmospheres of comets are made out of, also with spectroscopy. But we've also had spacecraft that have gone and actually snatched little pieces of comets, and we have a pretty good idea what they're made out of.
So then actually, since we talked a little bit about meteorites, to make a really bad pun, how do we use those to sort of ground truth the observations we make with
well, the idea is, we make these inferences from telescopic observations, and then we have meteorites on the ground, but we really don't know where the meteorites have come, which asteroid they've come from, usually. We had a very lucky event back in 2008 when an asteroid discovered with a telescope in Arizona, they predicted that it was going to hit 20 hours later in the desert of Sudan, near Egypt. And it did. And in those 20 hours after it was discovered, but before it hit, a lot of amateur and professional astronomers got their telescopes pointed at the thing and took spectra and measured other things about the asteroid in the sky. And then the thing came down, and they've collected about 1,000 meteorite fragments from the thing when it hit. And so we now know what that asteroid was made out of, because we got 1,000 pieces of it. and we can compare with the observations and see how well we did.
Very cool. So, so we've talked a little bit about sort of where asteroids are in the solar system. But are they? So I guess an important message to take away is that they're not just strictly between the orbits of Mars and Jupiter.
Yeah, that's right. I see the picture up here that is sort of about the sizes of asteroids, and I think Rusty showed a somewhat similar picture. But the big thing on the left is the asteroid Vesta, the second largest asteroid, and you see a big bulge sort of to the lower right, and that is the central peak of a huge crater on Vesta that's about as big as Vesta. And then we have a string of smaller asteroids shown going down toward the bottom. Where asteroids are located, there is a picture we have of, or several pictures of that, if they can be put up. Okay, well here's something somewhat similar to a diagram Rusty showed, but let me point out that this diagram shows where every known asteroid is, or was, last Friday. Every dot is a known asteroid and the position in the solar system. You're looking down on the top. The little yellow dot in the center is the sun. And the little yellow dot is the sun. The green asteroids are the main asteroid belt. The red ones are those that have been kicked out of the main asteroid belt. And I think another diagram or two will show. Okay, well this is a close-up. The symbols show the orbits, show where Earth and Venus and Mercury and at the top Mars were last Friday, and they're pretty much in the same place now at this scale. And this shows the fact that we really do have a lot of red dots floating around in space near us, so we live in a shooting gallery. And the next picture here, now at the bottom, well you see the little thing in the upper left, which is what I just showed you, but at the bottom, along the line at the bottom, you see the Sun, Earth, Mars, and Jupiter over here in the lower right. And the asteroids are distributed, as you see, going from the Sun out towards Jupiter. How high they are in the diagram shows whether their orbits are just like the Earth's in the same plane of the Earth's orbit, or whether they're tilted like that. And the higher they are in the diagram, the more tilted their orbits are. But you can see that the main asteroid belt is that bunch of stuff in red and yellow in the middle. There's a bunch of asteroids out right near in Jupiter's orbit. They're called the Trojans. But there's little red arrows at the bottom, and those are places where the asteroids go around the sun in a sort of even fraction compared to Jupiter. They'll go around twice when Jupiter goes around once, and Jupiter's mighty gravity produces gaps you see in that vertical gaps you see in the distribution, or you see clumps actually at Jupiter's orbit and elsewhere. But in those places, the big forces of Jupiter kind of kick asteroids out. There are gaps there because they've actually been sent into Earth-crossing orbits or crashing into the sun, or maybe ejected from the solar system, but that's an unstable place. And so that's how we get asteroids from the main belt into closer to the Earth where they can be dangerous.
And speaking of closer to Earth, would we also have an image about near-Earth asteroids?
Well, here's a picture of a different picture than the one that was shown earlier of Itokawa. This is the asteroid visited by the Japanese spacecraft a decade ago. And as you see, unlike many of the asteroid pictures you've seen that have asteroids covered with craters, you don't see craters on this thing. What you see are boulders, and this is really a boulder pile about 1/3 of a mile across. And it's kind of a typical near-Earth asteroid, we think. We haven't visited very many of them, and maybe some others look different from this, but remember the gravity is extremely small. Something as small as 1/3 of a mile across has almost no gravity, so these boulders and gravel and so on are just kind of resting together very, very lightly. It's not a big, solid, rocky thing that you might imagine. It's a very special place, and most of these asteroids are like that come close to the Earth.
So I guess the last question and
Yeah.
is, where did these come from? How did asteroids and comets form?
Well, the way asteroids formed has been briefly discussed earlier, but people have been drifting in and out here and drifting in and off the internet streaming. Basically, all the planets, there is a diagram, I think, if you can put it up. Okay. Yeah, there we go. Up in the upper left, you see the planets, and how the planets formed is by getting a lot of small planetesimals, they're called, smaller bodies that grew in the dusty and gaseous solar nebula 4.5 billion years ago. But not all of these small things actually made it into forming the planets. And in particular, between the orbits of Mars and Jupiter, Jupiter's gravity really kind of stirred up the velocities so that instead of these things coming together gently and forming something bigger, they were stirred up to higher velocities where they crashed into each other and smashed up. And so it's essentially a planet that didn't form. You were wondering about that, but I'd say it's sort of a planet that didn't form, and a lot of debris left over. And similarly, comets are debris left over from the formation of the outer planets, Jupiter, Saturn, Uranus, and Neptune.
All right, well, very good. So unfortunately, I don't think we have quite enough time for Q&A, but thank you, Dr. Chapman.
Okay, thank you.